All right, finally, we got the recorder to work. So last Friday, I went to the district-wide AI summit. Okay, is there any interest, any questions you might want to ask about the AI summit? We talk about, all kinds of topics related to AI and, basically education because it is a Los Rios kind of event. So there are people demonstrating how to use AI, how students are using AI. There are students explaining how they are using AI. So what are you guys interested in? Like how to use agentic AI to kind of do all your homework just by a prompt. You can search and find anyway. You don't need me to tell you about that one. Okay. What about job opportunities? Would that be anything useful to you? So I went to a workshop that was hosted by AWS, like Amazon AWS people, and they are saying that there are jobs. They really have to find people. They are looking for people to work for them using AI to develop software. So I will kind of point you to a web page first, which I'm sorry that is a little bit embarrassing. You'll find out why it's embarrassing. It's called a Kiro, okay? Kiro.dev. Okay, so what is embarrassing about this website or web page? What is a prototype? This is not from a mom and pop shop, around the corner, selling your grocery. This is Amazon. Amazon actually made this tool, but it's an agentic AI development tool. The person who was making the presentation, he actually uses this tool, to kind of develop software. And he said, there are not enough people um, who are qualified to use AI in software development. Okay, so I think that sounds a little bit interesting, right? Because everybody is complaining AI is taking our jobs. There are no jobs left, no jobs for, recent graduates. In fact, there is a report about, the outlook for 2026. 2026 computer science job outlook, and it's not good. Okay, so long-term growth, blah blah blah. Okay, but you can probably find it, at some point. But basically, the prediction is for 2026, the job market is even tighter than 2025. Yes. How about what? Computer engineering? It might be a little bit better. You have to look for that, because I'm not getting a whole lot of feed about computer engineering. But anyway, getting back to Kiro, the tool, okay? So as it turns out, these agentic tools, they can help a little bit, okay? But the thing is, they cannot deal with anything too complex, okay? If it is complicated, it would generate some code. It's not going to do what you want it to do, and then you can waste like days, weeks, and whatnot to try to tweak it, and it just won't work. Okay, so the tools are there, but they're not sophisticated enough to really replace people. So what does it mean to you? Okay, the first question, okay, does these tools make it easier to become a software engineer? The answer is actually no. The answer is actually makes it harder. Why do you think it is harder? Okay, it's easy. Many of you are taking CISP 430, right? Okay, just make a half-ass, effort in the next homework assignment and give it to a fellow student and go like, "Can you help me fix it?" That's kind of the deal with AI agentic tools. Okay, I'm not sure you guys are getting it or not. Are you guys getting it? Okay. So writing your own program is hard. Debugging somebody else's program is harder, especially if that other program is not even written by a person. It's written by a tool. Okay, so if it's written by a tool, it doesn't have a problem with, oh, I don't need to make your functions. You know, Instead of breaking up the functions into like 20 to at the most 40 lines per function, it can give you a 300 line function because it can deal with it. The question is, can you deal with it? Are you guys starting to get the gist of what is happening? So, with tools like this, okay, the problem is it will generate some code for simpler problems, but it cannot handle larger problems. So when the problems get more complicated, you have to read the code to find out what's wrong with it. And it's not even your code. It's not even code written by people. So the skill set to do this is actually higher. Now, is the productivity higher? The answer is possibly. Okay, not always, but possibly, because it can get the entry level code done. Okay, I don't really have any incentive, okay, to learn how to do Android programming. The reason why is because the framework is complicated enough. If I just want to make a hello world program and I want to do it myself to figure out, every single line of code to get an application to print hello world on my Android device, that's a lot of work. I don't want to do that. So this kind of environment can be helpful. Give me a template for a program that does a very simple thing. Do not even try to specify the logic. Just show something on the screen. So I would use that, okay, because that can save me days of time, okay? Or if I have a dialog box, okay, and I say, okay, if somebody types something in a dialog box and click this button, I need it to trigger an event, okay? Do I really want to learn the API to capture the event? Not really. But do I want to specify the code of what to do with the content of the dialog box after the event has happened? Yes. Okay. So there are things that are difficult for us because it involves a lot of details. And then there are things that we can do much better compared to a tool like this because it involves complicated logic. So the key is you have to be able to work with tools like this and not be over dependent on the tool. Okay, when something doesn't work, you have to figure out why it is not working. So to understand all of this, okay, this is actual a recommendation. It's not a joke. Okay, the next time you have something to turn in CISP 430, okay, exchange the program. Okay, have another person to try to help you debug a program because that is, I think, what this is heading. Okay, so the requirement to become a successful software engineer is actually more. You need to be more proficient at programming with your analysis and also with critical thinking than before, because there's no easy coding left. Okay, yes, no, it will give you an answer that is wrong. It's like a calculator that gives you wrong answers sometimes. So you have to find out why it is giving you a wrong answer, under what circumstances it give you the wrong answer, and then diagnose and fix the tool. Would you like a calculator like that? It is an AI problem. Yes. But that's also where the jobs are heading. Okay, so this is what I got out of the AI summit. Okay, other than there are a lot of people who are just opposing to the AI, the use of AI, and they recommend everybody not to use AI. Yeah, good luck with that. So anyway, I think that little bit of information can be helpful. Am I going to tell you what you need to do, to become successful or to prepare yourself to actually land a job at some point? No, I'm not going to do that because I don't know how to do it. I think a lot of this has to do with motivation. So I have to say this: people who are missing right now in this class, yep, and also people who come to this class, maybe not feeling that they're learning anything relevant. That's actually a part of it too. Attitude is important. Okay, aptitude is also important. Um, So the good news is there are jobs. Okay, Amazon, the person from Amazon explicitly said that they are having problem hiring people. So that means there are things they need to do, and they cannot find the right people to do it. So that's the good news. The bad news is the education system itself, by itself, may not be producing the people who are qualified to take on these jobs. So what do you need to do? You cannot change the education system, I mean, not by yourself. So what do you need to do? What are you going to do? Huh? Do stuff on your own time. What kind of stuff are you talking about? Well, related to getting a job in the future, it would be something related to using an AI tool to so that you understand what it is like to use an AI tool to write software. At the same time, you're going to learn the limitations and also what skill set you need to have in order to become successful. That is what you need to do. When you're passionate about something, that is true. When you're interested in something, you engage more and you can probably develop a better skill set. But I'll give you this counter example. Yes, I just used the term counter example because this is, after all, a discrete math class. Okay, give you a counter example. No matter how passionate I am about basketball, I will never make it to the NBA. So I do have to point that out. Okay, passion is good. Okay, but there is a certain degree of aptitude that is necessary in order to succeed. So there's that. Alrighty. So we're getting back to the boring stuff. Okay, hopefully you guys are not considering it too boring. So what we're going to do, last time we talked about, Tech and Pat competing for the same job, okay, because the company is downsizing, and by the way, they are also downsizing too. Okay, all kinds of company are downsizing. They are letting go of people. So that means the bad news is by the time you graduate in about 2 years-ish, 2 to 3 years from a four-year university, there might be a lot of people floating around because they lost their jobs. Okay, so that's the bad news. The good news is, you know about this already. Okay, I told you what I have learned in the AI summit, just last Friday. So that means that the good news is you might be able to prepare yourself for the time when you graduate and you need to land a job. Okay, one of the key thing is internship. So AWS, okay, the guy from Amazon AWS also told me about the internship program at Amazon. Okay, he said that most of the positions they become available in December. Okay, so those become available in December for preparation of the following summer. So you need to kind of catch that. Okay, just go to the various websites, look for internship. Okay, because it usually is kind of like that. They want people to apply, somewhere in the winter, okay? But the job or the internship is actually for the following year, typically in the summer. So that's what you need to do, okay? Internship is super important, okay? But internship won't help you unless you impress your boss during your internship. So that is the second thing, okay? Just because you land an internship is not automatically saying, oh, I will be hired by the time I get my bachelor's degree, because you have to convince your boss, your supervisor, okay, that yes, I'm so qualified, I'm so good at my job, even as a student intern. So by the time I get my bachelor's degree, it is a good idea to hire me back as a full-time employee. Okay, so that's the other side of why internships are important, but you have to do something to make it meaningful. Is that okay? So I'm going to help you take a quick look at Amazon, okay, Amazon AWS internships, okay, and see what we can find. They have a certain page just for internships. So there you go. Okay, fine. All right. So I would at least go there and figure out, what is available, okay, what they have to say about the internship program. And if they say, okay, we don't have any openings right now, but it will be available, you know, there are 20 openings. Yep. So view open roles, okay. So They actually have an office in Sacramento area as well, but I don't think you want to kind of limit your choices to just that. Oh, they have one in Hong Kong. Hmm, interesting. So right now, it doesn't look like they have anything in the US. Okay. Yep. It doesn't look like they have anything in the US. So we look for interns. But at least you can get an idea of what type of internship they have. Data center technician intern. And this one is about hardware and network diagnosis, followed by physical, what, repair. All interns will be exposed to independent work and in the team. Okay, so if this is the kind of internship is available, the question is, what do you need to do? I mean, this is obviously not in the US. I think this is in Germany, but keep an eye out on job openings or internship openings. I think that's going to be something that you can do. All right. So that being said, okay, we're going to go back and talk about stuff related to this class. And last time we talked about comparing algorithms, okay, how my 386DX computer is beating Pat's super duper, latest and greatest computer because I chose an algorithm with a much better time complexity. Okay, so that's where we kind of left off. Okay, so what we'll do today is really kind of talk about, asymptotic, estimates, and I have no idea why sometimes it will render, the math equations correctly right away, and other times it won't do it. Okay, a refresh gets the job done. All right. So asymptotic characteristics. So f of n, is the actual time complexity of an algorithm. So let's just say that it will give you down to the millisecond, actual time given a problem of size n. But guess what? F of n usually is really ugly. Okay, it's not going to be a clean type of function, so it makes comparison not very easy. And g of n is usually a much simpler approximation of the time complexity. So f and g hopefully are related. Okay, one is an estimate of the other one. So now what we want to figure out the relationship between the actual time complexity, which is f of n, versus some kind of g of n, which is an approximation of the time complexity. So are we doing okay so far? We have two functions. F of n is the actual time complexity. G of n just kind of give you a rough idea of the time complexity. But the nice thing is g of n is easy, like n squared, okay? N log n, or just log n. That's easy. F of n is kind of messy, okay? It has a constant portion, one portion that's proportional to n, one portion that is proportional to the log of n, and so on. So one is clean, easy to read. The other one is a little bit messy. So to do that, we are going to have to introduce a few concepts. The first one is called supremum. So a supremum is defined like this, okay? So this is the notation. S is the supremum of x if and only if P of Sx and for all S prime, P of S prime x implies S is less than or equal to S prime. Okay, so let's go back a little bit, okay? So we want to say, okay, what is A then? Okay, because A is mentioned here. A is a superset, X is a subset of A. So A is a partial order, okay? So now we go back and go like, did we talk about partial order? When did we talk about partial order? Relations. That's right. Okay. So if A is a partial order, that means what properties are true within um, what properties are true for a relation, let's say less than or equal to. Reflexive, transitive, anti-symmetric. I think that's one more. It's only three. Yep, you're correct. It's only three. Symmetric is not one of them. And comparable is only needed for total order. That is correct. Okay, So in this case, less than or equal to is the relation, and then we use less than or equal to as a relation for the set over A. Okay, so now we take a subset X out of A, and we want the supremum of X, which is a subset in A, is defined like this. So now the question is, what does that mean? What is P of something? So P, the predicate P is only here because we like to have it, kind of separate, because otherwise it just makes the expression super duper, long and difficult to understand. So we're going to take a look at, what is P of yx first, okay? And which is defined like this. That's just the definition. It is not derived, it's a definition. So what does it mean when we say for all x as an element of uppercase X, which is the set X, which is a subset of A, um, X is less than or equal to Y? You know one concept that is really, really close to what this is, but it's not exactly the same. So, no, it is not a relation. So if you are to define, the relationship between y and x, okay, like this, okay, if this is the relation, what do you think is a concept that you already know is kind of related to p of yx, but is not exactly it? Maximum. Okay, if y is the maximum of all the elements in X, then this property is, guess what, automatically true. Does that make sense to you? Let me say that one more time. Okay, if you find that y is the maximum of X, okay, does that make this property true? Y is already known as the maximum, so we say for every X in the set X, okay, X is less than or equal to Y. Yeah, that would make it true. But it also works for all the values that are greater than the maximum, right? Okay, so examples. Okay, I can see you guys are not understanding the. So this x is really just a notation as an element of this x here, and this x is a subset of A, and A is a set where the less than or equal to relation is a partial order. Yes, yeah, so this x is referring to this x over here because we need to have this relation too, right? The little x, you mean this one? It's you can look at this as a temporary variable that is needed in order for us to relate each element of x with y. So that's what the little x is. The lowercase x is really just a, huh? Yeah, 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 similar to e. Yep. There was another hand. Nope. Okay, alrighty. So P of yx is kind of saying that it's essentially saying that y is the upper bound of the set x. Okay, then you guys go like, okay, let's think about this a little bit. Okay, I'll give you a scenario, and because it is important to understand this part. Okay, so let me pick a mouse pad here. All right, so that's not for this class, but this one is. Okay, so we'll look at x as just a bunch of random elements. Okay, say integers. So we have 14 in it. We have 90. We have 3, and then we have 61. Okay, that's how uppercase X is defined. Okay, and now I'm asking you. Okay, I'll continue to show what is P of yx. Okay, so now I'm going to ask you, what about P of, let's do the obvious one first, 90x here. Okay, what is the result? Okay, what is the value of P of 90 comma x? We know that x is just a bunch of integers. Okay, first of all, is this x, does it meet the requirement? Is it a subset of a larger set that is partially ordered by less than or equal to? Hmm? X is, I mean, X is a set, okay? It cannot be ordered within a set. The question is X a subset? Okay, so let's go back to the definition up here. We want A to be a partial order. So the question is integer as a set, is it a partial order with respect to the less than or equal to relation? Okay, is less than or equal to a partial order defined over as a relation defined over integers? In other words, does it meet all the requirements? Okay, let's think about it. Is every integer less than or equal to itself? Okay, is less than or equal to transitive with respect to integers. If A is less than or equal to B and B is less than or equal to C, does that mean that A is less than or equal to C? Yep. Okay. Is partial ordering, I mean, excuse me, is less than or equal to anti-symmetric? If A is less than or equal to B and B is less than or equal to A, then A and B must be the same as integers. Yep, so it meets all requirements. So that means integers is a partial order at least using the relation less than or equal to. Is that okay? So think of this A over here as the set of all integers, which is typically represented as a fun-looking Z. So now we look at this X over here, and I don't know why. Okay, there we go. So now we look at this X over here, which is defined like this. Is that a subset of integers? It's just kind of random, right? But it is a subset of integers, okay? So now the next question is, so that means it is meaningful to ask this question, because in order to ask this question, X itself has to be a subset of another set that is partially ordered by some kind of less than or equal to relation, okay? So we have met all the requirements. So now we just look at this here, and then we are asking, if I pick everything from this particular set, is that thing less than or equal to 90? Okay, well, then it is true. Are we good so far? Okay, so I can give you some obvious answers why, when it is not true. So what about this one? It's 89, okay? So P of 89 comma X is going to return what kind of value? False. Yep, exactly. So now I'm going to ask you another question. What about this? Mm, okay, well, plug it in, okay? Is 14 less than or equal to 900? Yes. Is 90 less than or equal to 900? Yes. About 3 for 30, 61? So it is true. It doesn't matter. That's not required. Nobody asked for that. Ah, that is the trick, okay? So it's not really limited to the maximum, okay? The upper bound does not have to be a tight bound, okay? So 90 as a maximum is called a tight bound, okay? This is as low as you can get and still make the predicate P to return true. But P itself is going to be true for any number greater than or equal to 90. It is only looking for what we call an upper bound. So the concept of an upper bound is related to maximum, but is not exactly the same. Okay. So now are we comfortable with P of yx, what that means when it is true? Okay. If it is true, it simply means y is an upper bound of x. Okay. So now we look at the supremum, okay? So S is called a supremum of X, okay? I need to assign the symbol S so I can refer it on the other side. If and only if S is an upper bound of X and for all S prime that are also upper bounds of X, S is supposed to be less than or equal to S prime. What does that mean in the context of, this particular example here? What does it mean when I say, what about the supremum? Okay, the supremum of x in this case is what? It is a very specific value. Okay, so let's name a few um, upper bounds of this particular set. Okay, and we have identified a few already, right? Okay, what about P of 91? Okay, true. Okay, so what we have seen is 90 is an upper bound of x, 89 is not an upper bound of x, 900 is an upper bound of x, 91 is also an upper bound of x. So that means you can have an infinite number of upper bounds given a really small set like x over here. What are we asking for? What are we looking for? We are looking for, a specific upper bound that is less than or equal to every other upper bounds. In other words, give me the smallest upper bound. I'm not sure what you're asking. Yes, you mean you mean here? I'm not sure what you mean by can it not be separate. Huh? Okay. You can come to the projector and point. Are you sure? Okay. Well, but this is the simplest way I can express it. Okay. It means, okay, for all the S primes that are not upper bounds, forget it. I don't even care about those. Okay. But if S prime is an upper bound, I need it to be greater than or equal to this S over here. I'm trying to define S. I'm trying to find the property of S, which is known as the supremum of X. Okay, so given in this case, we are dealing with integers, and X is just this little set here with only four integers. What is the supremum of this X over here? Hmm? So, no, it is the lowest of the upper bounds. Which ones are upper bounds? This is an upper bound. 90 is an upper bound. 89 is not an upper bound. 900 is an upper bound. 91 is an upper bound. So now I'm asking, of all the upper bounds possible, which one is the smallest? 90. That is correct. So in this case, okay, because if we're dealing with integers, supremum is the same thing as maximum. Okay, maximum of the set. Yep. So the supremum of x is basically the same thing as the maximum of the set x. Okay, are we doing okay so far with that concept? Yep, but it does not have to be the case because we can have a partial order. Now, in the case of integers, the supremum of x is the maximum of x only because it is not only partially ordered, it is totally ordered. Okay, so being totally ordered means the supremum of x is the maximum of x. But you can have a partial order where the maximum or the lowest upper bound is not um, the maximum. Okay, do you guys want to kind of take a look at that particular scenario? Nope, it's not a for statement. It's not a for statement. But do you guys want to take a look at that scenario? Okay, so I can give you a partial order. Okay, so let's take a look at a partial order. And in fact, we're going to take a look at a particular A. Okay, so we'll say A has five elements. Okay, A, B, C, D, E. Okay, so there are five elements in A. We are going to define the relation. Okay, so less than or equal to is a relation, and I can do this. Okay, we can say, we know that A is less than or equal to B. We know C is less than or equal to D. We know that A is less than or equal to E. We know C is less than or equal to E. And we'll just say that we know B is also less than or equal to E. Okay, so A, B, A, E, C, E, B, E. And then we also need a reflexive. So we need AA, BB, CC, DD, and EE in it. Okay, so that's how less than or equal to is defined in this particular set. So we are not talking about the ASCII code of A, B, C, D, E and how they relate. A, B, C, D, E is just representing five some kind of element in a particular set A. Is that okay? All right. So now I ask, okay, so now I have to choose a subset of A, and we'll just say, okay, the subset of A is X, which is only A, B, and C. Are we doing okay? Yes. But, huh? I put what twice? Oh, EE. Okay, here. Thank you. Good catch. Good catch. There we go. Okay. So we are picking a subset X of A. Okay. Are we all agreeing that X is a subset of A? Cool. All right. So now I ask you the question. What is the supremum of this X over here? So we know that A is less than or equal to B, C is less than or equal to D, A is less than or equal to E, C is less than or equal to E, B is less than or equal to E, and then A is less than or equal to itself, B is less than or equal to itself, C is less than or equal to itself, D is less than or equal to itself, and E is also less than or equal to itself. So now I need to find something that is greater than or equal to every single one of these elements. It is E, okay? Say again. But that's the whole point because it doesn't have to be. The upper bound is not required to be in the set. Hmm? Yes, we did not have the. Well, because A is the set of all integers. So in this case, A is the set of all integers. Yes, but I don't care because X is okay. Okay, look right here. Look right here. Okay, I need to find. Okay, Y only has to be greater than or equal to everything in X. So the question is E greater than or equal to A? Is E greater than or equal to B? And is E greater than or equal to C? Okay, let's check it out. Yes, A is less than or equal to E, C is less than or equal to E, B is also less than or equal to E. Are we good? Doesn't that meet all the requirements already? Yes. Yep. Okay, so okay, so I skipped one step. Okay, so let's go ahead and do this. Okay, so P of A X. Okay, okay. What is that? Is A is everything in X here? Um, is everything in X less than or equal to A? No, there's no confirmation, okay? So you can pick something like D, okay? D is not even mentioned other than that it is less than or equal to itself. Can we confirm that D is less than or equal to A? No. So that means this has to be false because there's no confirmation. Is that okay? All right. So we look at B of Bx. So now the question is, if you look at the relation as it is defined on line 13, do we see that B is A is less than or equal to B? Yes, confirmed. Great. What about B is less than or equal to B? Yes. What about C? Can we confirm that C is less than or equal to B? No, C does not even appear to relate to B in any way. So that means the answer to this question is false. Are we good so far? Okay. And then we ask another question. How about C? Is everything in the set less than or equal to C? Okay. We know that C is not. If C is only confirmed to be less than or equal to itself, right? So that means I cannot say that A is less than or equal to C because AC is not a tuple here. BC is not a tuple here. Okay, so that means the answer to this question is once again false. Now we go to D. Okay, what about D? D is a loner. It is only less than or equal to itself. I cannot confirm that A is less than or equal to D, or B is less than or equal to D, or C is less than or equal to D. So that means the answer to this question, whether D is an upper bound of X, is once again false. So now we go to E, and then we ask the very same question. Do we confirm that A is less than or equal to E? Yes. Do we confirm that B is less than or equal to E? Yes. Do we confirm that C is less than or equal to E? Yes. Woohoo! We have our winner. This is the only one that is true. Hmm? What about the E? It doesn't matter because X only has A, B, and C in it. D is not even in X. Yep. We only have one S prime. We only have one S prime because there's only out of all the elements of X, only one is less than or equal to E, and that's after looking at A, because A has A, B, C, D, E in it, right? So we're looking at every single element of A, and then we ask which one is and which one is not an upper bound of the set X. And even after we ask that question, we can only confirm one thing, which is E is the only one that is an upper bound of X. So if it is the only one, it has to be the smallest one too. Is that making any sense? Hmm? Okay, so S has no predicate because it is the definition. We are trying to define S. There's okay. After the if and only if, what about it? Doesn't have what? Because there's only one single S. We only want to know whether S is a supremum of X. S given any value of S. S is a supremum of X if and only if S satisfies all of those properties. So that's why S itself is not quantified because we are trying to define, under what circumstances, okay, under what condition is S considered to be a supremum of X. That is the condition. No, it doesn't change because this is the very definition of what a supremum is. The first condition, what? You mean this using integers? The 90 on, sorry, say again. Say again. Yes, because it's totally ordered. So in the case that A is totally ordered, then the supremum is also the maximum. But in case of this a and this relation less than or equal to, then it doesn't touch it. The upper bound does not even touch any of the elements of x. So I probably would not recommend using a physical analogy to look at this. Okay, this really is abstract. Certain things are just abstract. Yes, and that's part of what you're getting into. Computer science is abstract. Yes, in the relation. Okay. Okay, so let's look at that scenario. Okay, so I'm gonna have to kind of copy and paste it because I don't want to contaminate this particular example. Okay, so we look at this, and then we look at another scenario. And okay, so tell me what else you want to add to it. So we want to add AC and also BC. Okay, so now we have to be a little bit careful because if we're adding these two, then we also want it to have um, BD should be in it because we need it to be transitive, right? So we need to be careful when we introduce new stuff to it. And also AD should be in it too. No, yeah, so AD needs to be in it because we have AC, we have CD, and it needs to be transitive, so AD has to be in it too. Okay, so I think we're good here. We're keeping X the same. So now we ask the question, okay, is A can A be can A be an upper bound of X? The answer is false. Okay, because AA is here, BA is not here, CA is also not here, so we know the answer to this one is false. What about B? Okay, so BB is good. Okay, what about AB? AB is here, that's good. What about CB? CB is not here, so it is still false. Okay, what about C? We like C, okay, because AC is in here, BC is in here, CC is also in here, so CX would then be true. Very good. And now we look at D, okay, so the question now, so D is also going to be true because it is because of transitivity. So, but let's double check, okay? So can we find AD in it? Yes. Can we find BD in it? Yes. Can we find CD in it? Yes. So that means P of dx or D being a one of the upper bounds of x is also true. Okay, very good. And E is still the same because we haven't really removed anything related to E. So now we have three upper bounds. Okay, so P, the predicate, is only confirming whether a particular element of A can be considered an upper bound of X. That's the only thing it's asking. Okay, so now when we look at the supremum, now it is no longer E because now we among C, D, and E, we have to figure out which one is quote unquote the smallest. So C is less than or equal to C, that's good. C is less than or equal to D, which is also good. And we actually have multiple answers in this case, okay? Because we can certainly, okay, so let me double check this. Okay, we have to confirm all of those. So we have to say that the supremum does not even exist. Oh, okay. So C does, okay, yep, it's we have that here. So C would be the supremum of X. But you can see how we can set it up so that the supremum is not even in X or it is in X. So it depends on how less than or equal to is defined in the partial order. Is that good? All right, so I'm gonna record a note to self. This would make a great question in the final exam. Yes, Okay, so once we have identified that C is a upper bound of X, D is an upper bound of X, and E is an upper bound of X, we are now comparing just between the C, D, and the E. In other words, we're looking at, do we have this? Yes. Do we have this? Yes. Do we have this? Then we have just confirmed that, you know, P, we have just confirmed that C is an upper bound of X. Okay, that's good. And we also have confirmed that for every other, no, I shouldn't say other, for every upper bound S prime, this S or this C is less than or equal to the upper bound in question, the S prime. Okay, so you have to learn how to read the notation and extract the meaning of the notation on your own. Okay, I would refrain once again from using analogies to answer to understand these type of things because I would go by the definition. I would spend the time to understand the definition. Okay, because there's no easy way to express abstraction because if there was, we wouldn't need abstractions to begin with. Abstractions are not here to make our jobs harder. It is here because it is a necessary tool to express certain concepts. Are we good so far? Are you are you seeing better with that? Yes. Okay. Did you forget your glasses or contact? Is that why? No. Okay. Because you can actually make a pinhole camera out of just doing this, and then you can see things in a sharper way because of the pinhole camera effect. But then everything get dimmer too. So that's not a pinhole camera. A pinhole camera means the aperture is the size of a pinhole. That is not the size of a pin, unless you're talking about a pin from the perspective of giants. Another tip, the next time we have a solar eclipse and you want to look at the eclipse, obviously do not stare into the sun, okay? But what you can also do is the same trick, okay? Use your hand to make a pinhole camera, and then the sun goes in, okay, and then the projection will be on a piece of paper, on the ground. And you can actually see the eclipse of the sun on a white piece of paper safely by using your hand as a pinhole camera. Hmm? Say again? I cannot hear you, sorry. On the paper, what about? Yes, it does work. Yep. hmm Because I did it in the previous solar eclipse. I just went outside and just do this and go like, oh, okay, I can see the eclipse. Alrighty. So are we understanding the concept of supremum? Okay. All right. So infimum is kind of the opposite. Okay. So if you compare, supremum versus infimum, the only difference is we flip around. Okay. So we define Q as a predicate. And in this case, for every x in the set x, y has to be less than, not greater than, or equal to x. So infimum is the minimum if the set A is a total order. Okay, are we doing okay so far? Because it's the flip side. It's really the exact opposite. Q of yx is true if and only if y is a lower bound. Because P is looking for upper bound, Q is asking is Y a lower bound of the set X. Are we good so far? The logic is exactly the same. Okay, one is looking for upper bound, the other one is looking for a lower bound, and then of all the lower bounds, I need the lower bound I, which stands for which is infimum, to be the largest of all the lower bounds. So we are looking for a tight bound in this case. If A itself is totally ordered with respect to the less than or equal to relation, then the lower bound, excuse me, not the lower bound, but the infimum is also going to be just known as the minimum. Okay, so one thing you can do, because we are only working with real numbers and also integers, so supremum is the maximum, infimum is the minimum. Are we good so far? Okay, all right. All right, but the concept of infimum and supremum, they are applicable to some random relation like the ones that we just talked about. Okay, so if I give you some random a, whatever less than or equal to that is randomly defined, but it meets all the requirements of a partial order, and I choose a subset, then you should be able to answer the question of what is the supremum or the infimum of the entire thing. Yep. Say again. Say that one more time. The formula of it is in the reading material. Are we good so far? Yep. Only needs to be partial ordered. So A and X are relating exactly the same way as before, except Q is a new definition, and then the notation infimum is also a new definition. Question? Mm-hmm. It is for every I prime. You're correct. Yep. Yep. I messed that one up. Let's fix that. Infimum. Okay. This is why I like GitHub. All right, so we are looking for the definition of infimum. And we go. And I also use a different notation here using a colon instead of parentheses. So I'm going to fix that too, just so that everything is a little bit more consistent. So the I prime is supposed to be here. And then we commit changes. Okay, commit changes. And then it will take GitHub a few, probably about a minute or two to rebake the new notation. So we'll give it some time. Right. Well, while it is baking, okay, all we have to kind of remember is this I here is supposed to be I prime. That's going to be fixed in a few minutes. All right. So now we talk about the limit of a sequence. Okay. So the concept of a limit is not unsimilar to the one that you have learned in calculus. Okay. So in this case, we are looking at, so you're given an infinite sequence, okay? So that means you have x0, x1, and so on, and all the elements in the sequence are real numbers. So you can make the assumption that these are actual real numbers, okay? So the question now is, if I claim that k, for some particular, a single value k, is known as the limit of x of I as I approaches infinity, what exactly does that mean? In other words, this is the notation, but I need to know what it means. Are we good so far? Are we understanding the question? Okay, this is the notation. I need to know what does it mean. So that means k is a unique value that satisfies the requirement that for all epsilon that is greater than 0, and epsilon is an element of a real number set, there exists an m as a natural number such that for all j that is greater than or equal to m as a natural number, the absolute value between k, which is this k over here, minus the x of j, and j is coming from here, is less than epsilon. All right, so that's the definition. What does it mean? Huh? Yep, calculus is based on the concept of limits. So let's go ahead and dissect this like really step by step. Okay. So let's just say that I choose a particular epsilon. Okay. It only has to be greater than zero. It cannot be zero. Okay. You can look at it as an error or a buffer. Okay. You can think of it as a buffer. Okay. And I need to find, so, okay, first of all, I choose an epsilon. Okay. Once I choose the epsilon, I have to find m, which is an index, such that for all the elements in the sequence, for all the xj's where j is greater than or equal to m, the error between the xj and the limit k they have to be less than epsilon. That's the definition. Are we understanding this or not? This is also why pre-calc is a requirement to take this class, because the concept of a limit is important. But the concept of a limit can also be expressed using just quantifiers. So are we understanding the concept or not? I can give you an example. Okay, would that help? Okay, we'll go with a simpler example. Okay, so we're gonna make a spreadsheet because after all we have a whole lot of calculations, so having a spreadsheet is going to be handy. So this is created in the shared folder for this class, 2025. Today is November 17th. Okay, so we are just going to look at, okay, I want to find one. So we'll look at, all right, so column A is going to be the index, which I can say, okay, we use 0 as the beginning because it has to be a natural number, right? 0 is the lowest natural number, so we have to start with that. And then on the other side, we can just say, okay, we are looking at 3 plus, um, let's just say, uh, 2 divided by 3 plus whatever this thing is. Okay, so that's a particular value. And then we look at the next index. Okay, so in this case, the xi's are related by a certain formula. They don't have to be, okay? But in this case, they are. So we'll just say, okay, this is whatever that thing is plus 1. And then the relationship between columns A and B stay the same. So are we doing okay so far with this? Okay. So we are going to make it kind of go to a relatively large index, okay, just so that we can see the effect, okay. So you can see that at some point it's still decreasing, but it's decreasing slowly. Are we good so far? Okay. So now I'm asking if I pick a particular epsilon, okay, so let's go ahead and pick an epsilon. Um, hmm, I need to define the epsilon somewhere else. Okay, we'll put the epsilon over here. So this is my epsilon. We'll just say the epsilon is 0.25 for no particular reason, okay? Because I just need the epsilon to be greater than 0 as a real number. So is 0.25 a real number? Is it greater than 0? Well, then it is an eligible epsilon, okay? So now the question is, what is the error or what is the difference between is each x of j, which is column B, and k, okay? So now we also have to kind of find a k, okay? It's like, okay, so what do you think this k is going to be? Just from the trend of it, what do you think it is? Okay, what do you think k is? What is the limit? Is 3. Yep, okay? So we are suspecting, okay? We'll just say that we suspect the limit is 3. Okay, are we good? All right. So just for, to make things a little bit easier on myself, I am going to give this particular cell a particular name. And you can do that. You can go to, I think it's data, named ranges. Okay, there we go. We'll just give it a range and we'll define G1. We call this our epsilon. Okay, epsilon. How do you spell epsilon? I cannot remember. I typed the notes, but I cannot remember because it's never really spelled out. But I can do that here. Okay, we can look at this. Epsilon. Okay, epsilon. Okay, epsilon. Not that one, this one. So now we just call this epsilon. Done. And this one we'll call it k. Okay, just because it's the limit. Or we can just call it limit too. Okay, fine, we'll call it limit. So we call this the limit. Okay, there we go. All right, so I need to now look at the absolute value between the limit and the x of j, okay, in this case, or all the indexes. So now we look at the absolute value of whatever this thing is minus what we think is the limit. Is that okay? Are we good? Are we relating the spreadsheet to the concept that I'm trying to explain? Okay. All right, cool. Double click. It autofills you all the way down to the last item. Kind of handy. Okay, so now we have to compare column C with the epsilon. Okay, so now we have to say, how does column C, is it less than the epsilon? So now we say epsilon, epsilon. There we go. It is handy. Okay, because I don't have to name the cell anymore because the cell actually has a name, so it's kind of more symbolic like this. Okay, we just double click that. Okay, so can someone tell me, what is a potential candidate for that m in the expression? In other words, if you go back to the notes here, I say that there has to be an m as a natural number so that everything, all the natural number that are greater than or equal to m makes this less than true. So what do you think is a good candidate in this case? Just looking at this screen here. Hmm? Say again? No, it's not a 3.25. It has to be a natural number. It would be 6. Less than. We need this to be true. So this is the index. 6 is the first index that makes it true. But can I pick, like 13? In other words, if I choose m to be 13, would that still be true? Okay, it is still true because everything after that, they're all true, all the way down to the last one that we have. Is that okay so far? So you guys go like, well, attack, you just pick something that's easy. Let's pick something smaller, right? So I would just pick something that is random, but it is smaller, okay? So 0.1, 3762. Okay, that's smaller. And now we ask the question, can we find an m that makes this true? And we can see that it's right here. So when epsilon is 0.13762, and we suspect the limit is 3, that means m has to be something that is greater than or equal to 12. Any natural number that is greater than or equal to 12 can serve as the m in this particular expression. You know what? I only need one because it's an existential quantifier. So can I find at least one? Yes, done. Okay. So far we have only confirmed that 3 is in fact the limit of this thing here. Are we good so far? Okay. So the problem with the limit of a sequence is if you have a sequence like this, then there's no limit. The limit simply does not exist. Is that okay? So now let's take a look at what happens when x of I is defined to be -1 to the power of I. Okay, so we go back to the spreadsheet. Okay, there we go. I'm gonna shut, kind of Turn that off right there. Okay, so now we start a new sheet, sheet 2, and we do the same thing over here. Column A is really just the index. Okay, so this is going to be this one plus 1. Okay, no big deal over here. And this one doesn't need to be very long. You will see the pattern. So column B is the value of x of whatever column A is. So this would correspond to x of 0. So we go like, okay, we are looking at the power function. And is it power or power? I cannot remember. I think it's power. And this is -1 raised to the power of whatever column A has on the same row. Okay, so we have 1 because -1 to the power of 0 is 1. And then you go like, oh, okay, we are just alternating, right? -1, 1, -1, 1, -1, 1. So now I ask you, okay, what do you think is the limit of this particular sequence? Name anything, okay, and we'll check whether it works or not. Hmm? It does not exist. There's no limit to this particular sequence. Okay? You go like, okay. So when we're looking for the asymptotic um, value of a function, some functions simply do not converge. Okay? So the function that we saw a little bit earlier in sheet 1, it converges to 3. And then when we look at the one in sheet 2, it has no convergence. So that means, okay, so how do we describe this? Okay, it doesn't have a limit. So the answer to that question, we have 5 minutes left, which I think is more than enough. So now we define limit superior. So limit superior, which is lim sup, is defined like this. Okay, so the limit superior of a sequence of x of n as n approaches to infinity is defined to be the infimum, but to you it is minimum, the minimum of the maximum of as n is for all the subsequent k xk, and then for n that is greater than or equal to 0. So this is n, okay, and this is k. So are we understanding what this means? Okay, we'll kind of work on this kind of one step at a time. The K is basically saying, okay, we are this n is on the outside. It is essentially a quantified number thing here. So n starts with a 0, and then it becomes 1, it becomes 2. So as n changes, this k also changes because k has to be greater than or equal to n. So we are basically saying, okay, when n equals to 0, we are looking at all the maximums starting with x0 and then x1 and then x2 and then x3. And then when n is 1, then we're looking for all the maximums again, but this time we start with x1. When n equals to 2, then we start with x2, x3, and so on. And then we look, so at the end, we have a whole bunch of maximums. Okay? The limit superior is the smallest of all of those maximums. Are we good so far? So let's go ahead and translate this into our spreadsheet. We'll kind of give it a try. I might remember how to do it. I may not remember how to do it, but we'll give it a try. So now we want to find out what is the maximum from this point on. Okay, so the maximum from this point on is simply the maximum of whatever this cell is. Okay, and then all the way down. So to specify that range, we have to use, I think it's called offset. So when you use offset, you have to specify where we are beginning. So that would be, it would be the same cell over here. So that's going to be this number. And then you specify offset. And then you have to specify how many after this. So that would be count A of the entire column A. and minus this particular row number plus 1. And then this is only one single column. So the offset is now specifying the range where the maximum applies, and it is just itself. So now I think this works by extending it, okay, like so. So because this particular function is monotonic as well, okay, so that's why if you start counting from, say, index 3, everything after that is smaller than it. So when you look at the maximum of whatever is smaller than it, it's really just itself, okay, it is its own maximum. So now you have to look at the minimum of the entire column E. So we now have to compute what is the minimum of column E, and that is up to this point 3.007, because we are not done with this sequence. Okay, it is supposed to keep going and going. Okay, but you can kind of see the trend of this. So this is the lim sup, or the limit superior. This is the individual supremum starting from index 0. This is the supremum starting with 1, and so on. And this is the minimum of all the supremums. Okay, so I think in the final exam, I can give you questions like, okay, I give you a particular sequence, okay? It is not mathematically defined. It is just me giving you a bunch of numbers, okay? And then I'll ask you about those questions, okay? Is P of yx true or false, okay? What is the limit superior? What is the limit inferior? And so on. So that forces you to really have to understand the concepts, because that really is part of what this class is about, is to understand the concepts, because all we are doing with this is only introducing the definitions, the concept and the definition. We are not using this to prove any theorems. That would be the job of an upper division computer science class that you are going to pay a lot of money to take somewhere else. So that is not my problem anymore when you take that class. But I'll try my best, okay, to get the concepts to you so that by the time you take that class, you will still remember the definitions, so that you can focus on what else you need to learn in the upper division class, and not to have to go back and go like, what is the limit superior? I have no idea of how to read a quantified expression. So that is my job. So we are continuing this on Wednesday. I'll see you on Wednesday. And looks like it's not raining anymore. So if you have cool stuff to do, I guess you can do it now. And for those of you who like to drift your car, this is good. just be just be safe.